let's talk about Euler's formula. A little while ago, I made a short video about e to the pi I. Here I want to exploit this identity a little further and actually dive into some of the mathematics behind it. E to the pi I is a version of a more general formula created by Leonhard Euler used for writing complex numbers. Now, originally for this video, I was planning to somehow explain the concept of an imaginary number. I was going to do it by considering a negative number to be something like a hole in the ground. But honestly, it was just more confusing that way. Instead, I think it's much better to just picture complex numbers for what they actually are. An absurdly complicated way of graphing points on a plane designed by crazy mathematicians in order to deal with the ridiculous technicality of the square root of a negative number. Imagine you want to hang a painting on a wall. A normal person would just measure out something like 2 feet from the door and 6 feet from the floor, and just hang it there. But a mathematician has to designate the middle of the wall as 0, the origin. To the right, regular numbers are measured out. To the left, negative numbers. Now, for the top and bottom, instead of simply having another axis like a regular Cartesian graph, they decide to use magnitudes of square root of -1. Why do this? Because mathematicians are insane, of course. Top is positive, bottom negative, and now any point on the wall can be written as this crazy equation here. And instead of having to write the square root of -1, we can just simply use the letter I. Just don't confuse it with other situations where an I might be present. Okay, so this is your basic way of writing the complex number. The next way to express this number is to use the polar form. We are summoning the powers of trigonometry for this one. Because this wasn't complicated enough yet. Cosine is relegated to the real numbers, assigned to the imaginary, and r is the radius, or the hypotenuse. I won't be explaining how to derive this. It can be easily found on the internet. The third way to write a complex number is using Euler's formula. Getting this result isn't so obvious and is perhaps one of his most famous accomplishments. Euler originally demonstrated how you can achieve this result using Taylor sums, but I won't be diving into these here. There is also a proof using derivatives, but I won't be doing that either. Instead, in this video, I want to show you how you can obtain this form using this guy's formula. Abraham de Moivre. So yeah, another one of those guys with those names that gets butchered a lot. God, look at this guy. No wonder he practiced the dark arts of complex analysis. So let's look at his formula. The idea is that when you multiply complex numbers, it is easier to use the polar form. This allows you to simply add their angles together and just multiply the radius. So this means that when you raise the complex number to some power, it means that you are multiplying the angle by that same quantity, which means we get this nice equation here. Let's save this formula for later. Now, in order to tackle this expression, we can consider a more general situation, that of a regular number taken to some complex exponent. For starters, since we are using addition here, we can break this thing apart. We can see that this just becomes some regular number. But let's just ignore it, assuming a is equal to 0. Now this guy can also be simplified because we can pull the b away from the I. And n to the power of b will also become just another regular number. Let's just stick with n to the I to make our lives simple. Now, originally I went through an elaborate set of arithmetic to arrive at a natural logarithm in order to get us closer to Euler's form. So this can equal to this thing. But then I realized that using a logarithm for the exponent of that same base results in the same thing that it's raised to regardless. And that this is an obvious thing in mathematics that everyone knows already. And now that we have this situation, we can finally apply the Moivre's theorem. This means we can shove this x here, and these other x's just go down there. And by the same reasoning, we can pull out theta, which would imply that this should be equal to 1, and that theta is equal to the natural log of n. And when n is e and theta is equal to 1, we happen to arrive at Euler's formula. Pretty neat. No Taylor sums, no derivatives, and when pi is theta, we of course get the famous identity itself. Now I think this is pretty cool. It almost looks like Abraham was very close to finding e pi I. But of course these guys didn't have the internet back then to double check their stuff. But you do, so I encourage you to see if you agree with my math. Did I get it right? Or is it all just smoke and mirrors and I missed something crucial? Remember, I'm not a teacher and this is not an educational video. I'm just an amateur math enthusiast. I hope you all have fun taking this video apart. Like, subscribe, enjoy, and thanks for watching.